Hi, Dr. Hamdan and everyone. So today we are going to present on the steady-state non-isothermal reactor design on adiabatic condition. Um, our group members are respectively Li Yang, who is me, Muhammad Haziq, Ahmad Saidi Suib, and Muhammad Ifan. So basically for this video session, we are going to discuss on the general energy balance, the derivation of the general energy balance equation, and also for the adiabatic energy balance equation for the adiabatic condition, and also for the examples for the adiabatic condition. So for this slide, we are going to discuss on the general energy balance of an open system. So basically this is the equation of itself, and firstly is the rate of accumulation of energy equals to the rate of flow of heat to the system from the surroundings minus the rate of work done by the system on the surroundings plus with the rate of the energy added to the system and minus the rate of the energy leaving the system, and also these two have to be times with their own mass flow rate, inlet and outlet. So we can treat this as inlet and we can treat this as outlet. So basically what I've just said just now, this is the equation that I said just now, okay? The terms are Q is the heat transfer, WS is the shaft work, this one is the inlet that I said just now, okay? This one is the outlet, and this one is accumulation. Since we assume that this is a steady state equation, steady state process, therefore the accumulation is equals to 0. And here you are, this is the new equation we have. Okay, basically this is the new equation that we assume that the accumulation is equal to 0. As you know that in energy balance we have learned the formula for the inlet and formula for the outlet, where we have to times each of the enthalpy for each reactant and product with their own molar flow rate for inlet as well as for the outlet. So we have to have the summation of all of this and substitute inside these two equations, then we can get the overall equation. So basically for this FA, we have learned the FA formula from the stoichiometric chapter 4 in this course, okay, and we can substitute all of these formulas inside this FA, FB, FC, FD, and FI, and soon, okay, we'll get this long equation over here, where this part is the inlet and this part is outlet. And as you can see here, the outlet part has consists of the heat of reaction. Why heat of reaction? Because normally outlet part is the products. So if you say the products is the reaction has occurred. So meaning if the reaction is occur, exothermic reaction may occur and the heat is released from the system. So this is called the heat of reaction. Okay, heat of reaction. Okay, basically heat of reaction is having this formula. So if we want to shorten this whole equation over here, we can get this one, the summation of this, the inlet, okay, and we can summarize this one as the HR after summarizing now. Okay, so as for this one, it's a reaction in the inlet and outlet for varying heat capacity. Just now is the constant heat capacity, where the heat of reaction does not consist of the Cp changing value. This one we have to consider for the Cp change value, as they didn't assume that the value of the heat capacity is constant, meaning that the enthalpy is not constant. All right. So in this context, we have to add one more term here, which is the formula for the change of the enthalpy for each species. And then we have to these all formulas are the same, and we add the formula for the Cp, and we will get this one. Voila, we will get this, the new formula, and we insert it into the formula before, and we assume that there is no short work, and therefore we get this equation over here. Right? Okay, so basically, okay, that one is just a general idea for the energy balance. So now we are going to move on to adiabatic energy balance. For adiabatic energy balance, normally we assume no work. As for other parts, we also assume no work because normally in the reactor we don't have any moving parts. Okay, and this one is the all the moving parts. All the moving parts is very negligible. So we just ignore it. And in adiabatic operation, the heat transfer is there's no heat transfer, so therefore Q is equal to 0, and letting the the initial temperature is equals to the final temperature, because that there is no, they say that they assume that there is no net flow of the there's no net change of the temperature, because there is no heat transfer, so there is a big possibility that the temperature does not change. So better still we assume as same temperature. And as you can see here, this is the equation that I said before, and you substitute here and here. I mean not substitute, you just switch position for this, and you get x as this one, and t for this one. X is the conversion, t is the temperature. So these two you can be used for the examples of problem of the adiabatic operation. As for this one, this is the mole balance that will be used for the problem also, mole balance equation. So there is another context that the CP value here, the CP T minus R here is very small as compared to the HRX value. So therefore, we can just ignore this one. And therefore, when you plot a graph of XEB is basically just a conversion energy balance, okay? Conversion value of energy balance. T value is this one. Since we have cut off this one, then we left out the T minus T naught. Therefore, you'll see that X is directly proportional to this one, so we always get a linear equation. Okay, since we have neglect this one, so I just want to show a graph to you that we neglect this one so that we get a linear one. Okay, that's all for this part. This is only the derivation for you guys to understand more. Next, I will pass on to Ifan to talk more about the examples in terms of the adiabatic operation. Thank you.
Okay, now I will explain on the example for the adiabatic operation. This question is on PFR, working in a reversible reaction between species A and species B. The inlet of the PFR is species A and also an inert, and the ratio between the inert and the species A is 2:1. So the question asks to plot XSE, temperature and rate over volume graphs, and we will use polymath for this question. This is all the requirement or the specifications given in the questions for the reactor. We can see that the concentration of the inert is 2 to the concentration of initial species A, because as mentioned in the question, the ratio is 2:1. So we use times 2. And the initial temperature for the reactor is 300 Kelvin. As we are using polymath, this is how it is look like after we key in all the data into the polymath system. And after that, we run the data and we will get this table. As we can see in the table at number 20, we get the final conversion is around 66%. Now let's go to our graphs. The graph is the XSE versus volume graph. The blue line indicates the conversion, while the red line indicates the equilibrium conversion. Equilibrium conversion is the highest conversion that can be achieved by the reactor. And we can see that the equilibrium conversion decreases until it meets with the conversion, and finally the conversion reach around 66%. Now let's go to our second graph, which is the temperature versus volume graph. As mentioned in the question earlier, the initial temperature is 300 Kelvin. And we can see that the temperature increases as the volume increases. But at around 6 centimeter cube, the temperature stops increasing and remains constant at the end until the end of the reactor, until the end of the reaction, at around 360 Kelvin. So this is our final graph, the rate versus volume graph. The rate increases initially until it reaches its peak at between 5 to 6 centimeter cube, but it decreases very steeply until the end of the reactor. The value of the rate is around 0. And this is our references for this presentation. That's all from us. Thank you.